In the previous video, we talked about the precise fundamental definition of the derivative. And in doing so, we derived the definition of the derivative from two different perspectives. In this video, we're going to look at a third form of the derivative that's very commonly used. Specifically in scientific publications, I feel like you see this form a lot. So, okay, let's start by reviewing what we learned in the previous video. So the derivative is a pointwise property of a function. For a given function, f of x, some function f of x, with the derivative, you're asking the question, what is the derivative of f of x at some point within the domain of f of x? At some point a within the domain of f of x. And so from the perspective of the curve f of x, you're asking, what is the derivative of f of x at point P on f of x? With the coordinates of point P being a, comma, f of a. Okay, but then you could ask this same question for some other point in the domain of f of x. Well, what is the derivative of f of x at point B? So where, with respect to the curve f of x, you would be asking, what is the derivative of f of x at point J on the curve, on the f of x curve, with the coordinates of point J being B, comma, f of B. And so from a completely general perspective, so like for the definition of the derivative, you're not thinking about a tangent line or a velocity or anything like that. In complete general, the pure fundamental definition of the derivative is, so you've got some function that you're interested in, finding the derivative, as well as some point of interest within the domain of the function. You take the difference quotient of that function with respect to that point in the function's domain, and then you take the limit of that difference quotient as the denominator approaches 0. And then you've got the derivative of the function at that point. So what's the difference quotient of a function at a point? What's the difference quotient of f of x at A or at point P? Okay, the difference quotient is just the change in output with respect to change in input between point P and any point on f of x, not including point P, and on either side of point P. So to write the difference quotient, we just think about some arbitrary point Q that's anywhere on f of x, as long as it's not point P itself. Now, the location of Q is variable. It can be anywhere, but the difference quotient is just the change in output between point P and point Q with respect to or divided by the corresponding change in input between point P and point Q. So the difference quotient is you just take this distance and divide it by this distance. But again, point Q is not fixed at some position. You write it in such a way that it's variable. So if this distance is delta x and this distance is delta y, then the difference quotient is just delta y divided by delta x. But again, the location of Q is not fixed. Q can be anywhere, as long as it's not on P. And so once you have the difference quotient written, the derivative is just the limit of the difference quotient as the denominator approaches 0. But as the denominator changes, so does the numerator. Delta y is dependent on delta x. If you change delta x, you're ultimately changing the location of Q on the curve. So you're changing delta y. So with this limit, what you're ultimately doing is you're finding the change in output with respect to the change in input between point P and some other point Q that's infinitesimally close to point P, coming from either side of P. That's the ultimate meaning of the derivative. And so now what we saw in the previous video was that there's different ways you can set up the coordinates of point Q and point P. And so there's different forms that you can come up with for the difference quotient. And thus there's different forms that you can used to derive the derivative. And so one form was to say that you leave the coordinates of point P as a comma f of a, but you say that the coordinates of point Q are given by x comma f of x. And it's just a coincidence that this happens to be the cross, like a y-intercept. Okay, and so from this perspective, then the difference quotient is you say f of x minus f of a divided by, that's delta y, and then divided by delta x, which would be x minus a. There's the difference quotient from this perspective. And so the derivative then is just you take the limit of the difference quotient as the denominator of the difference quotient goes to 0. So in this case, that would be as x approaches a. So there's one form of the derivative of f of x at point a. All right, now we saw another way you could derive the derivative, by saying that, so we're still going to leave point P as just a comma f of a. You know, we could potentially change the way we label point P, but we're going to leave that as a comma f of a, but we'll call the delta x distance just h, meaning it's just a distance of the x coordinate of point Q from the x coordinate of point P. And that would make the y coordinate of Q, because the coordinate location then, the x coordinate location of point Q is a plus h. So the y coordinate of point Q is f of a plus h. So therefore the difference quotient is f of a plus h minus f of a all over, and then just h. Here's delta y, here's delta x. And so the derivative then is just the limit of the difference quotient as the denominator of the difference quotient approaches 0. So as h approaches 0. So now in this video, we're going to talk about a third way that the derivative is formulated. And a lot of people feel that this is the best formulation of the derivative. Again, I've personally found that I see this form a lot in scientific publications. And I think what's so popular about it is it shows the meaning of the derivative from the most fundamental perspective. The derivative is an instantaneous change in output with respect to the corresponding change in input. So for this third form, the difference quotient is set up in that, so, okay, the x coordinates of point P and point Q, you take the a coordinate of point P, and for the third form, the a is replaced with x1. Then the x coordinate of point Q is given by x2. And therefore, the y coordinate of point P is f of x1. And the y coordinate of point Q, again, this is a coincidence that point Q is lined up with this y-intercept, but the y coordinate of point Q is f of x2. So let's take a look at how this works. Suppose y is a quantity that depends on another quantity x. Thus, y is a function of x, and we write that y is equal to f of x. Yeah, so if you're reading through this for the first time, it almost sounds like they're talking about something brand new here, and they're really not. So like, suppose y is a quantity that depends on another quantity x. They're just saying, look, we've got some relation between y and x, and it's not just any relation, it's also a function. We're just saying, look, but we've got some function of x. We're not talking about a relation, because how can we talk about the derivative of a relation at a point when you've got two or more separate curves at that same point? Which curve are we talking about, right? You have to separate this into two functions and look at the derivative here and the derivative here. So all they're saying in this first sentence is we've got a function. Y is a function of x. Y is equal to f of x. Okay, and so all they're going to do is just set up the difference quotient, again, with point Q having coordinate x2 and y coordinate f of x2, and point P having x coordinate x1 and y coordinate f of x1. And the advantage of this is that you can label the distance from the x coordinate of point P to the x coordinate of point Q with a simple delta x. And same idea with the change in y coordinate from point Q to point P. you can just label it with a simple delta y. And so the overall difference quotient becomes this really simplified delta x over delta y, which it says, okay, this is the difference quotient, and it's called the average rate of change of y with respect to x over the interval from x1 to x2, and can be interpreted as the slope of the secant line, PQ, in figure 8. So yeah, I mean, if you're reading this for the first time, it's almost like they're talking about something brand new, but they're not at all, right? The way they state this, you've got, so this is called the average rate of change of y with respect to x. They've got this bolded here, and then they're calling it the difference quotient. So it's almost like nothing we've talked about so far in this section, in the previous video, like we haven't talked about the average rate of change of y with respect to x yet. We haven't talked about the difference quotient yet, but that's not the case at all. So here, this is the difference quotient, just in another form. This is the difference quotient, just in another form. Both of these are, without a doubt, the average rate of change of the output with respect to the input, or the average rate of change of y with respect to x. I guess maybe since we didn't use the letter y explicitly and the letter x explicitly, from that perspective, it's kind of different. But, I mean, no, fundamentally, it's the average rate of change of the output with respect to the input. That's exactly what both of these mean. You cannot have any type of derivation of the derivative whatsoever without starting by writing out the difference quotient of a function. The difference quotient is part of the inherent meaning of the derivative. Again, what the derivative is fundamentally is the limit of the difference quotient as the denominator of the difference quotient approaches 0. And the difference quotient is the average rate of change of the output with respect to the input over an interval. And so, again, what exactly does that mean, the average rate of change? Why is the term average being used when referring to the difference quotient, the average rate of change? Well, okay, the difference quotient is called the average rate of change because the interval is finite, which means that, like, even if you calculated a velocity as the change in position, so to indicate finite, we use this delta symbol, the change in position over a corresponding change in time, where the delta t was, say, a quarter of a second. Well, that's still an average velocity, a delta v, because you could technically analyze, okay, how much did the position change over the first eighth of a second, 0.125 seconds of that interval, and then analyzed how exactly the position changed over the second eighth of a second of that interval. And maybe those two changes in position with respect to time are different. So you have two different velocities at the beginning of the quarter of a second and at the end of the quarter of a second. And so what the overall delta v is over the entire quarter of a second is an average velocity, an average change in position with respect to time, right? So again, this is just another form of the difference quotient. But you can see how this form is potentially more popular because it's this very simplified and intuitive form of a delta y over delta x. And so now to get the derivative, all you're doing is just taking the limit of the difference quotient of a function as the denominator of the difference quotient approaches 0. So in this case, that would be it would be the limit as delta x approaches 0. And there you go. The limit as delta x approaches 0 of delta y over delta x, that's the derivative, which is it's the instantaneous rate of change of y with respect to x. You can see how general this form of the definition of the derivative is. Y can be any output variable, and x can be any input variable. But now I think the only downside of this form is that you might have noticed that you lose the information that you are still computing the derivative of the function at a specific point in its domain. So like in this case, the limit point a, the point of the derivative a, is replaced by x1, right? And so this form is sort of implying that x1 and x2 have the same level of importance in the derivative when technically they don't. Here, we're computing the derivative of the function f of x at the point x1 in the domain of the function. That's why it's f prime of x1, right? So keep that in mind as well for these two definitions, it was clear what the derivative point was. The point within the function, that single point within the function that we're trying to determine the derivative, the slope of the tangent line at this point. That was A. That was point A, x-coordinate A. But that's not as clear here with this form. Now, something else you want to keep in mind going forward about the derivative is, so as we get to different points in the course, I'm going to be making videos and talking about how you'll see people manipulate equations involving the derivative and the integral. They'll move variables around, switch one variable with another, take limits of both sides of an equation to turn certain pieces of the equation into a derivative, take integrals of both sides of an equation. And at first, it can be confusing as far as how exactly they're able to do this. So what you want to remember about any derivative is, so thinking about the difference quotient of a derivative, it's always the case that delta y and delta x are related to one another. Like we talked about at the beginning of this paragraph, y is a function of x. With any difference quotient whatsoever, the output variable in the numerator is always 100% of the time a function of the input variable in the denominator. And this is the reason why, as you let delta x approach 0 to determine the derivative, then delta y automatically must approach 0 at the same time. Like it's never the case with a difference quotient that as delta x changes, nothing happens to delta y. For example, I could say that we have a change in a variable, let's say the change in the price of the iPhone, delta P. Then I can also say that there's another change in variable corresponding to the change in position of my vehicle. Okay, well, I can't just say something like, let's take delta P and divide this by delta x. So now we have a difference quotient of this P with respect to x, and now we're going to take the limit as delta x approaches 0 and call this the derivative of the price of the iPhone with respect to the position of my vehicle. No, because P is not a function of x. These two variables are not related. So this is not actually a difference quotient. This is just a ratio of the change in the price of the iPhone with respect to the change in the position of my vehicle. That's all it is. And so the reason why you'll see derivations where professors are switching out variables in difference quotients and then taking limits to form derivatives is because the different output variables are all dependent on the same input variable. For example, for some system, you can have an independent variable of time. So you've got this, for this entire system, you've got this time axis, and so there could be a delta t, some change in time. Well, there's a lot of different variables that are related to time, right? And they can all be contained within the same system. A change in position is related to changes in time as velocity. You have changes in velocity with respect to changes in time forms acceleration. Energies, forces over distances, like impulses are related to time. You can relate forces to time. There's a lot of variables that are related to time. So you could think about the idea of having a delta x over a delta t as a difference quotient, and then you're doing some derivation and you switch out the delta x with a delta v, or even like a change in force magnitude or something, and now you have this delta x over delta t is converted to a delta v divided by delta t, and then you take the limit of this and get a derivative to get, and that would be an acceleration. The limit as delta t approaches 0 of delta v over delta t is like an instantaneous acceleration. Again, it's because all of these output variables are related to the same time axis. Now, but note that it's not like you could have two separate systems, one system from today and one system from 5 years ago, but both of those systems were related to time, but it's just two totally different situations. And you say, I'm going to bring in some position with respect to some time axis that was from 5 years ago and throw it on some unrelated time axis and start incorporating that delta x into some unrelated delta t. No, no. You have to have all of these data points related to the energies and the forces, etc., correspond to the same time axis. Okay. It says, we know that one interpretation of the derivative f prime of a is as the slope of the tangent line to the curve y is equal to f of x when x equals a. We now have a second interpretation. The derivative f prime of a is the instantaneous rate of change of y is equal to f of x with respect to x when x is equal to a. So yeah, I mean, like personally for me, I kind of find that the way the author of this textbook is laying this out is kind of confusing. It sounds like we're talking about something brand new here. Or it sounds like this new form of the derivative, this delta y over delta x difference quotient form, is the instantaneous rate of change of y with respect to x at x is equal to a, but the other forms that we talked about in the previous video don't correspond to this. That's not the case at all. It's all the exact same mechanical concepts, it just in different forms is all. So it says the connection with the first interpretation is that if we sketch the curve y is equal to f of x, then the instantaneous rate of change is the slope of the tangent line to this curve at the point where x is equal to a. This means that when the derivative is large, and therefore the curve is steep, as at the point P in the figure on the left, the y values change rapidly. When the derivative is small, the curve is relatively flat, and the y values change slowly. In particular, if s is a function of time, is the position function of a particle that moves along a straight line, then f prime of a is the rate of change of the displacement s with respect to time t. In other words, f prime of a is the velocity of the particle at time t is equal to a. The speed of the particle is the absolute value of the velocity. That is the absolute value of f prime of a. So, yeah, let me write this out. The limit and this is f prime of x1. So it's just that what they're pointing out here is that this form makes it much clearer that the derivative at a point is how much the y variable is changing with respect to the x variable at a given point is all. So you can think about that as it relates to the steepness of the curve, right? A steeper curve in the positive or negative direction. So a negatively sloped curve would mean that the delta y is negative, but if it's steep, then you have a large change in y for a corresponding smaller change in x is all. And what they're talking about here is you can distinguish between, you can have two slopes. One's a very steep positive slope, the other one's a very steep negative slope, but the absolute value is just giving you the magnitude of that. So in the sense of velocity, yeah, if you have a large velocity going in the positive direction and a large velocity going in the negative direction, then you could just talk about the speed, how fast you're going, which just means the absolute value of that velocity. But again, if we come back to these first two forms of the derivative, these are still the same exact idea. These are changes in output with respect to changes in the corresponding input, and then you're taking the limit as the delta interval of the input goes to 0. Nothing different whatsoever. Okay, let's take a look at this example. It says, a manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards of this fabric is C is equal to F of X dollars. So yeah, that's another thing I find useful about this form is that this is really intuitive when you're not dealing with time, like velocities, right? So you have a cost function. With this form, you can clearly see that the derivative is with respect to any output variable and any input variable, right? But again, though, the output is a function of the input. You can't just put some arbitrary delta up here. The change in the gross domestic product of the country with respect to the change in how many hours of night of sleep you're getting. No. You have to start off with an output as a function of an input. So what is the meaning of the derivative f prime of x? And what are the units? So this x is how many yards of fabric are produced, and then the c is the cost of producing those yards of fabric. So the difference quotient is a change in cost, the cost to produce X yards of fabric with respect to the total number of yards of fabric produced, and then you take the limit as delta X approaches 0. Now, but this is going to give you the derivative at a specific number of yards of fabric produced, X1. So what this means is that, at 10 yards of fabric, if you're going to produce 10 yards of fabric, and that's going to cost F of $10. Okay, well, what's the instantaneous rate of change of the cost of producing the fabric at that 10 yards of fabric point? You can kind of think about this as, if you produce an extra yard of fabric, what's going to be the increase in cost? That's technically not the instantaneous rate of change, because that's the average rate of change of the cost going from X equal to 10 to X equal to 11. So it's really technically more, if you produce the tiniest bit of extra fabric, more than 10 yards or less than 10 yards, what would be the decrease in cost if you went in the other direction, then what's going to be that slightest change in cost? And so, but like, you can't really think about, if I produce an extra thousandth of a yard of fabric, a millionth of a yard of fabric, what's going to be the change in cost? I mean, you don't really think about it that way. And so that's why they're saying here, in practical terms, what does it mean to say that F prime of 1,000 is equal to 9? So when you're producing 1,000 yards of fabric, that's going to cost a certain amount, right? Say that's going to cost $500. Well, in practical terms, F prime of 1,000 being equal to 9, you could think about it like, okay, if I produced an extra yard of fabric, it's going to cost me an extra $9. Or if I produced 1 yard less of fabric, so 999 yards of fabric, it's going to save me $9. That's a practical way of looking at it. You're not going to say, oh, the derivative means that if I produced 1,000,000,001 yards of fabric, it's going to cost me an extra, and then convert that to like some fraction of a cent. No. Which do you think is greater, F prime of 50 or F prime of 500? What about F prime of 5,000? So we have to think about the shape of the cost function here. What do we expect the shape of the cost function to be? So if we think about the shape of the cost function, so the domain of the input X is going to be any X greater than or equal to 0, because you can't produce negative yards of fabric. And then the cost is also going to be something greater than or equal to 0, because you're not going to get paid to produce fabric. You're not going to make money as far as expenses producing fabric. So, okay. What we would expect is some minimum fixed cost to where even if we produce no fabric, we're still going to have some expenses, like from the rent of the building and whatnot. Okay, and so in the beginning, the cost of manufacturing just a little bit of fabric, the first 10, 50, 100, 200 yards of fabric, let's say it increases something in a way like this, but then at some point, there's going to be like an economies of scale that's going to make this curve level out to where it still costs more. The more fabric you produce, it's always going to cost more, but the scaling of the operation means that for every additional yard of fabric you produce, it doesn't cost you, it's not as much of an increase in overall cost. But at some point, it becomes inefficient to produce so much fabric, and this is going to go back to a steeper slope. So as far as the derivative, we would expect that F prime of 50 would be greater than F prime of 500, which would be like in the middle here. And then F prime of 500 would be greater than F prime of 50. It's like right in the middle in that sweet spot, you have the most efficient operation of the entire manufacturing process. Okay, let D of T be the U.S. national debt at time T. The table in the margin gives approximate values of this function by providing end-of-year estimates in billions of dollars from 1985 to 2010. Interpret and estimate the value of D prime of 2000. So yeah, you've got this table of data points here, these different years, time T, these different years, and for each year, the corresponding approximate value for the U.S. national debt at the end of that year in billions of dollars. And so we can think about how, you could plot these data points like in Excel and then get a curve fit. What curve fit you choose would depend on, that's a topic for statistics, but perhaps the best curve fit would be like a polynomial curve fit or an exponential curve fit. But you get a curve fit, and with the curve fit, you'll have a d as a function of t, some continuous d as a function of t. Now, you might be thinking, well, okay, yeah, so when are we allowed to take derivatives? I mean, can we take derivatives if we just had a set of data points with no curve? I mean, can we take a derivative at a single point? We're going to talk about the idea of when you're allowed to take derivatives, when derivatives exist. That's the concept of differentiability in the next section. But just right now, imagine that we've got these 6 data points and we created a curve fit through the data points, and we have an equation, a continuous function that represents these data points. So what would we interpret as the meaning of d prime of 2000? Well, okay, what that technically means is it's the instantaneous rate of change of the national debt with respect to time. So whatever that d prime of 2000 is, it could be a positive or negative value. I guess it would be a positive value in this case. Well, if you increase the time, so if you went an extra second in time past January 1st, past New Year's, then the national debt is increasing by, but it's infinitesimal, right? So even a second is not small enough. You have to go nanoseconds, even smaller than that. So in practical terms, you're thinking about it as d prime of 2000 is if you went forward 1 year in time, the national debt would increase by the derivative value. Okay, so now here's the technical formula for the derivative of the national debt d prime at 2000 with the whole limit of the difference quotient at the time t is equal to 2000, the year 2000. But now they do an average computation of this derivative, d prime of 2000, but they do it in a way where they just do an interpolation, like an average interpolation between 1995 and 2005, and they get that. So an estimate for d prime 2000 is that's approximately $318 billion per year, which means that you interpret that in a practical sense that this derivative means that in the year 2001, the national debt increased by $318 billion. On average, though, that still would be on average going from 2000 to 2001. You could give a good average estimate in that the derivative is telling you that the national debt increased by $318 billion in that year. But an even better estimate would be to actually, again, you could go to Excel or go to MATLAB and get the most accurate curve fit of these data points. Get an equation, then take the derivative of that equation, plug in 2000, the year 2000. But if you want an even more accurate derivative, then you would need more data points. More data points combined with more accurate estimations of the national debt. Okay, so in examples 3, 6, and 7, we saw 3 specific examples of rates of change. The velocity of an object is the rate of change of displacement with respect to time. Marginal cost is the rate of change of production cost with respect to the number of items produced. And then the rate of change of debt with respect to time is of interest in economics. Now, here's a small example of other rates of change. In physics, the rate of change of work with respect to time is called power. Chemists who study a chemical reaction are interested in the rate of change in the concentration of a reaction with respect to time, called the rate of reaction. A biologist is interested in the rate of change of the population of a colony of bacteria with respect to time. In fact, the computation of rates of change is important in all of the natural sciences, in engineering, and even in the social sciences. And yeah, we're going to talk about this further. We're going to go into this even more in chapter 3. All these rates of change are derivatives and can therefore be interpreted as slopes of tangents. This gives added significance to the solution of the tangent problem. Whenever we solve a problem involving tangent lines, we are not just solving a problem in geometry. We are also implicitly solving a great variety of problems involving rates of change in science and engineering. Yeah, exactly. One of the reasons why they're wanting to define the derivative from a complete general perspective and not have it associated with any tangent lines or velocities is just complete general. The limit of a difference quotient is that we're going to see there's all kinds of applications of the derivative. There's all kinds of perspectives in which the derivative is applied. We're going to learn about a lot of these in chapter 4. But even past just this textbook, there's a lot of ways the derivative is used.